problem. We will straight away go for okay. Yeah, students, there is a problem in sharing the screen. So let us move to the board actually. Board is visible to you know.
Yes, sir, visible, sir.
Board is visible now. Okay, fine. So as I said, we will be seeing now how to derive E and V. What is E is electric field intensity and what is V is electric potential. And as I said, I am going to change or finite line. Okay, that is the going to take. So first, let us draw the diagram. Okay, for a straight line. Okay, uniform line distribution, right? And here at a point P, okay, a point P somewhere here. Okay, point P somewhere here. Now, what I am doing is from I'm joining here, okay, with an angle, and I am considering a small element at this particular point. I am joining it, and from here, I am making a join. Okay. Now the point is, this is actually okay. This is actually total length the conductor what we have taken here. Okay, what we have taken here is L, capital L, which we can take capital the conductor, and this distance I'm taking it as x. Okay, and I'm going to consider a small element here of length dl. Okay, the dl I'm going to consider at a distance of from the top. This distance is okay. Now can I tell the distance is what? In the distance total straight line line total length is L. I'm going to consider P somewhere here at a distance of x from the top. Okay, then I'm going to consider a small element dl. Okay, at a distance of small l from the top. So my question is, what is the remaining distance? What is the remaining distance that I get? Can anyone tell? See, this is totally x. This is l. So what will be? This is nothing but x minus l. Am I right? I'm going to consider two angles. So this angle I'm taking it as alpha 1. In turn, this angle I'm taking it as 2. and this angle I'm taking it as my theta. Okay, and this r I'm going to take, and this distance is h. So from this point to P it is h, then from here to P it is r I'm going to take. So this is my P point actually. Okay, so this is my x-axis. So I am going to resolve here. I am going to find what is the value of dEx here, which is my x component, and I am going to take the y component in this way. I am going to dEy, and I am going to join, okay, these two things, and dE. You got the point? So now my focus is to find the. This is the actual diagram. For this diagram, we are going to work out. Is it okay? So this particular diagram is, I'm going to call it as the line charge distribution. This derivation is very, very important. That's why I'm taking it. This one, and in the next class, we are going to cover uniform circular charged disk. Circular disk. That is also a very, very important thing. Procedure is, see here, my another point I want to convey is, if this angle is theta, then can anyone tell what is this angle? What is this angle? Yes, what will be the angle? See, this point is actually P. This point is P. Angle is theta again. Why it is theta? See, if this angle is theta, obviously I will get theta here. This angle will be C. Is it okay? So this is the point is that I am going to consider a uniformly charged line of length capital L whose linear charge. So I am going to write Q here, and I am going to take in terms of linear charge density. We have already seen charge distributions, linear charge distribution, surface charge density, then volume charge density, everything. So how to express charge Q in terms of linear charge, in terms of surface charge, in terms of volume charge, we know that, right? So I'm going to make use of that particular thing. And here I'm going to consider a small element dl, which I written here, at a distance L, from the charged line, from the top, as shown in the figure. Let capital P be any point at a distance R from dl. So distance between D and P is actually R. That is the actual I want to tell over here. Then here, what I am going to do is, I am going to find the expression of D. That is my task. Okay. So have you taken this diagram? Shall I make a move to the derivation part? We are going to make use of this particular diagram for our derivation. Don't forget this diagram. It should be near to us, and only we can derive. Okay. So what I am doing first is, I'm going to find the general expression of electric field at a point due to this linear charge. So actually, dE, I'm going to call it as, dE is actually Q divided by 4 pi epsilon r square. Why r square is, our consideration side is actually from point infinitesimal small element dl to P. So that particular distance is r. I'm taking it as r square. Okay. And now linear charge density means what is the value of Q? What is the value of Q that we have to consider? So actually, value of Q was rho L dl. We might be knowing it from our charge distribution discussion. So now dE will become this one. dE is equal to rho L. Is it visible to you? It's visible, I think. So dE is equal to Q by 4 pi epsilon r square. and Q I am going to write it as write it in terms of linear charge density. So it becomes rho L dl by 4 pi epsilon r square. Now I am going to resolve from our diagram. You can see I am going to resolve this dE component into two. Number one in x-axis, another one in y-axis. So here what I am doing is I am going to resolve dE in terms of x direction first. If I do it, will be equal to what angle I will get it actually? Can anyone tell? See, I want to find dEx. That means to this angle theta, this side is actually dEx. Am I right? Because this particular length and this particular length will be equal. So this is of what direction? Means normally we will go for sine theta, because sine theta is nothing but opposite by hypotenuse. So I can write dE sine theta. Same way, dEy is equal to dE. dEy means this side, which is adjacent side. So d cos theta, I get it. Okay. So now what I'm going to do is I am going to find these two answers separately. Okay. So first I'll be taking, for example, dEx. I'm going to, for example, you consider this dE. Okay. So if I want to find dEx, right, what the value will be is dEx equal to. So it's nothing but dE sin theta. dE value as rho L dL by 4 pi epsilon r square into sin theta. This value we know. dE value we know here. Into sin theta, I'm going to make some modifications. From the figure, what I'm going to do is, right, what I'm going to do is, see, for example, in this particular triangle, to come back to the picture so that you can understand. In this particular triangle, where x minus L, h and r, this right angle triangle I'm going to consider. And for this particular triangle, what is the value of, say, cot theta? What is cot theta? Normally, what is cot theta? Cot theta is actually inverse of tan theta. Tan theta means it is opposite by adjacent. So cot theta is adjacent side by opposite side. So for this one, this is opposite, this hypotenuse. This is my adjacent side. So adjacent divided by opposite. So I'll be writing like this. And if I interchange the values, it will become x minus cot theta. Right. So what I am trying to do here, I am going to replace this particular dl value, which is available in dEx expression, into something in terms of theta, because I am having sin theta here. Okay. For that particular purpose, I have written like this. And here, I am going to make a differentiation. So what will happen? X differentiation with respect to theta, actually. So what will happen? X will get vanished because L will become minus dl, h as it is. What is differentiation of cot theta? Differentiation of cot theta is minus cosecant square theta d theta. So what will happen, you know, 2 minus will get cancelled. L is equal to h cosecant square theta d theta. This is the value, I'll get it. Thing which we have to. Next case, what I am going to do is, in the same diagram, I am going to take, instead of cot theta, I am going to take sin theta. So what is sin theta? Sin theta is opposite side by hypotenuse, right? Opposite is h by r. That is my plan is, I am trying to replace r in terms of h. Okay. So what will happen now to r will be equal to h by sin theta. So 1 by sin theta is cos theta. It becomes r is equal to. So what I am going to do now is, finally, I am going to put this particular r value, this particular dl value in this particular expression. It's a very simple, but you have to take tan theta and cos, which we have to perform. Okay. just taking the answers of these two things. So my dEx will be equal to rho L will remain as such. In the place of dl, I'm going to write h cosecant square theta d theta already is there divided by 4 pi epsilon. In the place of r square, I am going to put h square cosecant square theta. So what it happens now is cosecant square theta with cosecant cancels, one h with another h gets cancelled. What is remaining is rho L sine theta d theta divided 4 pi epsilon h is the thing which is going to remain. Is it okay? Now we are going to find for the entire length. What I have done now is for dl, that is for small infinitesimal element, I have done this derivation. If I consider for the entire length of the conductor, entire length of the conductor, what will happen? We should not incorporate theta value. We have to incorporate component alpha. Okay. So for this particular one, what we have. So now we are going to find x. It's nothing but differentiation of dEx between some range. That range is very, very important. Here I am going to put for the entire length means alpha 1 to pi minus alpha 2. I am going to put it. Alpha 1 to pi minus alpha 2. See, the point is alpha 1 is the angle which is coming in this way. Okay, in say this alpha 2 is in elevation. இந்த ரெண்டு ஆங்கிளும் பாத்தீங்கன்னா ஒரே மாதிரி இருக்கும். இந்த ஆங்கிள் இப்படி வந்துருன்னா நம்ம இந்த பாக்கி இருக்கிற ஆங்கிள் தான் we have to pick. Okay, see this particular line has got a total angle of 180. So 180 minus alpha 2 is nothing but alpha 1. So alpha 1 here pi minus alpha 2, or in this case, or in this way also we can write like pi minus alpha 1 to alpha 2 also we can write. That's also correct. Okay, so now I am going to integrate this particular, which I got it for dEx, to get Ex between the range alpha 1 to pi minus alpha 2. That is what we are going to do. Okay, so if I do what will happen to Ex? So I am doing it at the top. Integration between the limit alpha 1 to pi minus alpha 2, and here that's it. Okay, so if I do what will happen? What will happen? That is the actual part. I am writing it here. See, Ex is this rho is a constant. 4 pi epsilon h is also a constant. Remaining is integration between the limits alpha 1 to pi minus alpha 2 sin theta d theta. What integration of sin plus minus cos theta, right? Minus cos theta. So it becomes rho L by 4 pi. This is minus cos theta between the limit alpha 1 to pi minus alpha 2. Okay, pi minus alpha 2. So finally what I will be getting is, because here one minus is there, I will be getting the expression like rho L by 4 pi epsilon h, and here cos of getting it. Okay, right? I am going to perform the same operation for Ey. Okay, only thing is you have to do for DE. See, go to this side so that you can understand. For DEY, we have already seen it is like DE cos theta. That is in the place of sin theta, wherever we have written it as sin theta here, we have to write cos theta, and we have to perform the same thing. We have to perform integration also between the same limits. If I do it, I will be getting Ey expression. Okay, Ey expression I will be getting it. So the expression of Ey, it looks like, so I expression rho L by 4 pi epsilon h. I'll be getting sine, okay, sine alpha 2 minus sine alpha 1 to be expression of Ey if I do the same sort of derivation, right? So this is the expression for Ex, I mean Ey I have written, and this is the expression for Ex what I'm going to get. This is the derivation. See, once you know how to find these two values, like what is Ex and what is Ey, we can get E totally. Am I right? Because we know it is the resultant component of Ex and Ey is nothing but E. So once we have derived E, we know the relationship. E is equal to minus del V is the relationship. Okay. Or in turn, E is known means what is V here is minus integration of E d r, or in the place of here H. If I do this integration, right, I can get potential. Okay, so here I am going to consider two cases actually. I'm going to consider two cases here. Case one, what I am doing is this alpha 1 and alpha 2 are available no? Here, alpha 1 and alpha 2. These two values are equal. These two values are equal. What will happen? You look at this expression. If these two are equal, what will happen here? Cos alpha plus cos alpha, you'll get it. What is cos alpha plus cos alpha is 2 cos alpha. So 2 with 4 can get cancelled. Okay. What happens here? Sin alpha minus sin alpha. Sin alpha minus sin alpha gets cancelled. So Ey term as a whole will be 0. Ex only will get it. Okay. That is the resultant E value actually. Second is what I am going to do is I am take alpha 1 and alpha 2 as 0. 0 means let us consider I am having infinite length content. That is the case, alpha 1, alpha 2 will be made 0. Am I right? If these two values are 0, what will happen again? Cos 0 I will get plus cos 0. What is cos 0? Cos 0 is 1. So 1 plus 1 is again 2. So we will get Ex value. What Ey? Sin 0 minus sin 0. Sin 0 is already 0. 0 minus 0 is already 0. 0 into anything is 0. So Ey will, and total E will be equal to Ex alone. That's all. So this is the actual derivation. And here, actually, you should understand one important point. From the derivation of E, okay, we have to, or we should be in a position to calculate potential also. Potential also we have to calculate. Okay, I hope you understood this particular derivation, right? Understood? Any doubts? Get it actually in mobile app also. Okay, so please have a look on your mobile so that you can understand what is topic that you can understand. Okay, so this is the actual point. Coulomb's law, those two problems, as time is up now, we cannot continue. And already you have completed. The only thing is epsilon or values, if they are mentioned, what we will do or how we will calculate, that actually matters. Okay, so it's not an issue. Do that on your own, right? So in next class, our plan is to go for charged circular disk. Okay, so this particular part is very, very important. Have a glance on it. If possible, I'll send you the recording link also. Okay. Okay, as we are in Google Meet, taking attendance in person, so a few more minutes.